People talk about living on the moon like it's a dream, a colony, a new chapter for humanity. And maybe it is. But here's what nobody puts in the brochure. The moon has been trying to kill everything that lands on it since the day it was born, and it's very good at it. This isn't doom and gloom. This is what the dream looks like up close. And here is a question. If you could bring only one item on the moon to save your life, what would it be? Let me know in the comments. I will pin the most creative answer. Now let's begin. Well, if you stepped outside on the lunar surface without a spacesuit, and we are never going to recommend you do this, you would not explode like some movies suggest. That's actually a myth. But what would happen is, in roughly 15 seconds, the oxygen in your blood would begin to deplete. The moisture on the surface of your eyes and mouth would boil off. Not because of heat, but because of the absence of pressure. Your skin would swell, and within about 90 seconds to 2 minutes, you would lose consciousness. Permanent brain damage would follow almost immediately. Death would come shortly after. That's just from the absence of air. But let's say you do have a spacesuit, a good one, NASA approved, tested to the extreme. Now you're protected from the vacuum. Problem solved, right? Not even close, because now we get to the temperature. On Earth, our atmosphere acts like a giant blanket. It absorbs heat from the sun during the day and releases it slowly at night, keeping temperatures within a range where life can survive. The difference between the hottest and coldest places on Earth's surface might be around 150 degrees Celsius, and that already feels extreme. The Sahara versus Antarctica. Hot and cold. On the moon, there is no blanket during a lunar day, which lasts about 14 Earth days. The surface directly in sunlight reaches around 127 degrees Celsius. That's roughly 260 degrees Fahrenheit. Hot enough to boil water, hot enough to cook food. And then the lunar night arrives, which also lasts about 14 Earth days, and the temperature plummets to around negative 173 degrees Celsius. That's negative 279 Fahrenheit, colder than liquid nitrogen. Let that sink in for a moment. The same rock, the same patch of lunar surface. In the span of a few weeks, it goes from scorching hot to cold enough to freeze almost any material we know of. That kind of thermal shock doesn't just destroy equipment. It destroys everything. Metals crack, seals fail. The materials we build with on Earth are simply not engineered for swings like that. And your suit, the one protecting you, it has to survive all of it. Now, here's where it gets really interesting and a little bit humbling, because you might think, okay, we're smart, we're humans. We've built buildings that survive earthquakes, submarines that go to the bottom of the ocean, satellites that orbit in the cold of space. Surely we can engineer our way around this. And scientists are working on exactly that. NASA's Artemis program, which is working to return humans to the moon and eventually establish a long-term presence there, is developing next-generation suits, shielded habitats, and survival systems designed for the lunar environment. It's one of the most complex engineering challenges in human history. But even with all of that technology, even if we solve the vacuum and the temperature, we would still be facing something that engineers find genuinely terrifying, something you can't see, something you can't touch, something that passes straight through the walls of your habitat as if they weren't even there. So you've made it this far, you've got your suit on, you've survived the vacuum, your habitat is keeping the temperature steady, you're breathing, you're alive, and you might be thinking, okay, what's next? What else could possibly go wrong? Here's the thing about the moon. It doesn't just threaten you with things you can see or feel. The most dangerous force up there is completely invisible. You can't smell it, you can't hear it, you won't feel it touching your skin. And yet, every single second you spend on that surface, it is passing straight through your body, through the walls of your habitat, through every layer of protection you've brought with you. And it's quietly, patiently tearing apart the very molecules that make you who you are. We're talking about radiation, and not the kind of radiation you might think of when you picture a hospital X-ray. Not even close. What you face on the moon is a completely different category, more powerful, more relentless, and in many ways more frightening precisely because science is still working to understand the full extent of what it does to a human being over time. Let's break this down from the beginning, because the story of radiation on the moon actually begins billions of years ago in the violent heart of a dying star. When massive stars reach the end of their lives, and we're talking about stars dozens of times larger than our own sun, they don't go quietly, they explode. These explosions, called supernovae, are among the most powerful events in the entire universe. In a single moment, a supernova can release more energy than our sun will produce across its entire 10 billion year lifetime. And one of the things these explosions fling out into the cosmos are particles, protons, helium nuclei, and heavier atomic cores, moving at speeds approaching the speed of light. Those particles travel. They travel for millions of years. They cross unimaginable distances. And eventually, some of them find their way into our solar system, into the space between the planets, and straight onto the lunar surface. Scientists call them galactic cosmic rays. Right now, as you watch this, galactic cosmic rays are traveling through space at nearly the speed of light. The most energetic of them carry as much punch as a well-thrown baseball compressed into a single subatomic particle. When one of those particles hits something, a wall, a suit, a human body, it doesn't just bounce off. It punches through, shattering the atoms it collides with, and sending out secondary showers of additional particles. It's like a tiny invisible bullet that turns into a tiny invisible shotgun blast when it hits something solid. And Earth, your home, protects you from almost all of it. Our planet has two overlapping shields that work together to keep you safe. The first is the magnetosphere, a massive bubble of magnetic force generated by Earth's molten iron core. This invisible shield stretches out tens of thousands of kilometers into space and acts like a cosmic deflector, bending the paths of charged particles away from us. The second shield is our atmosphere, that layer of gas we talked about earlier. Any particles that do make it through the magnetosphere have to fight through roughly 10 meters of air equivalent, which absorbs and scatters what's left. The result is that the radiation dose you receive living a normal life on Earth is roughly 2.5 millisieverts per year. That's the standard unit scientists use to measure biological radiation exposure, and 2.5 is considered completely safe for a healthy human being. Now here's where this gets genuinely astonishing. The moon has no magnetosphere, none. Scientists have found traces of small, localized magnetic fields in certain patches of the lunar surface, but nothing even remotely comparable to Earth's global shield. And of course, the moon has no real atmosphere either, which means those galactic cosmic rays, that storm of high-energy particles from exploding stars, they hit the moon's surface completely unobstructed. In 2019, China's Chang'e 4 lander, which made history as the first spacecraft to land on the far side of the moon, carried a specialized instrument called the Lunar Lander Neutrons and Dosimetry Experiment. It measured, for the very first time, the actual radiation environment directly on the lunar surface, and the numbers it recorded were stark. According to those measurements published in Science Advances, astronauts on the lunar surface would be exposed to roughly 200 times the radiation level of someone living on Earth. Let me put that into perspective. If you live on Earth for a year, you absorb about 2.5 millisieverts of natural radiation. On the moon, unshielded, you would absorb the equivalent in roughly 2 days. An entire year on the lunar surface would expose you to somewhere between 300 and 400 millisieverts, and that's without any major solar events. But the galactic cosmic rays are only part of the problem, because the sun itself is also a threat, and a far less predictable one. Our sun, for all its warmth and beauty and life-giving energy, occasionally loses its temper. During what scientists call solar particle events, or SPEs, the sun erupts in tremendous bursts of radiation. Magnetic fields on the solar surface collapse and reconnect with explosive force. Protons and other charged particles get accelerated to enormous velocities and fired into space. If Earth happens to be in the path of that blast, our magnetosphere deflects most of it. Our astronauts on the International Space Station get a higher dose than usual but remain protected on the Moon. There is no deflection. Research published in Planetary and Space Science found that a severe solar particle event could expose an unshielded lunar astronaut to roughly 1 sievert in a matter of hours. For context, 1 sievert is the threshold at which you start experiencing acute radiation sickness, nausea, vomiting, fatigue, and the beginning of what doctors call the radiation syndrome. At 2 sieverts, your body starts to struggle to repair itself. Above 6 sieverts, without immediate medical treatment, survival becomes very unlikely. And the terrifying part? These events are not fully predictable. Scientists can monitor the sun and provide warnings, but the advance notice can be as short as 30 minutes. On the Moon, you would need to get yourself into a shielded shelter within that window. Every single time. Now you might be wondering, can't we just build a thick enough shelter to block all of this? More metal, more material, more layers. And this is where radiation physics throws a genuinely nasty surprise at you. For the lower energy solar particles, shielding actually works quite well. Hydrogen-rich materials, plastics, water, food stores, clothing can absorb a significant portion of that radiation by colliding with the incoming protons and transferring their energy. The Artemis program's Orion capsule has a designated shelter space designed exactly for this, and engineers at companies like STEMRAD developed a protective vest called AstroRad that could cut the dose from a solar storm by roughly 40 to 60%. But galactic cosmic rays laugh at conventional shielding. Because of how unimaginably energetic they are, the heaviest cosmic ray particles can plow straight through almost any material. And worse, when they hit dense shielding like aluminum or steel, they shatter the atoms in the shield and produce a cascade of secondary particles. You might actually end up with more radiation exposure behind certain kinds of shielding than you would have had without it. Scientists call this the secondary radiation problem, and it's one of the most frustrating puzzles in space medicine today. According to NASA's Human Research Program, the health risks from long-term cosmic ray exposure include an increased probability of cancer, damage to the central nervous system, cataracts, heart disease, and degenerative diseases of the brain. And critically, many of these effects are not immediate. They accumulate silently over years and decades. You might spend a year on the Moon feeling perfectly healthy and only discover the consequences much later in your life. This is what keeps space medicine researchers up at night. And look, I want to be honest with you, the way I always try to be on this channel. Scientists are not standing still on this. Brilliant minds at places like NASA's Space Radiation Laboratory at Brookhaven National Laboratory are actively studying how cosmic radiation damages human tissue. Researchers are experimenting with everything from new shielding materials to pharmaceutical countermeasures, drugs and supplements that might help cells repair DNA damage faster. There are even extraordinary experiments looking at proteins from tardigrades, those near-microscopic creatures sometimes called water bears that have the remarkable ability to shield DNA from radiation damage. Early lab results show this approach could reduce DNA damage in human cells by around 40%. The universe is dangerous, but human ingenuity is relentless. And yet, even if we solve radiation tomorrow, there is another danger waiting for you on the moon that most people have never even considered. Something so small, you need a microscope to see it. Something that tore through the gloves of Apollo astronauts, jammed their equipment, and that one space engineer called the problem we don't fully understand yet, and that might be, quote, deadly L-right. You've made it to the moon. You've got your habitat. You've got your shielded shelter for solar storms you've accepted. With remarkable courage, honestly, that radiation is going to be a constant companion, a silent tax your body pays just for being there. You've made peace with the vacuum and the temperature swings, and the fact that Earth is a glowing dot in a black sky 384,000 kilometers away. You step outside for your first surface walk. The ground beneath your boots is grey, powdery. It almost looks soft like volcanic ash or fine beach sand after it's been bleached by the sun. You take a step and it puffs up around your boot, floating in slow motion in the low gravity, settling in a thin layer on your suit. It's almost beautiful, actually. This ancient grey powder covering the most famous surface in the night sky, you've just made contact with one of the most dangerous materials in the known solar system. It's called lunar regolith. Most people just call it lunar dust. And it is, without exaggeration, a nightmare, a microscopic nightmare that has already surprised and battered every mission that has ever landed on the moon, and that scientists and engineers today consider one of the most serious unresolved problems standing between humanity and a permanent lunar presence. Let me tell you what this stuff actually is, because understanding what makes it dangerous requires understanding where it comes from. On Earth, things get worn down. Rock faces erosion from wind and water and ice. Over millions of years, boulders become pebbles, pebbles become sand, sand becomes fine silt, and in that process all those tiny particles get their sharp edges rounded off. They become smooth. They become relatively harmless to breathe and touch because billions of years of geological processing have taken away their bite. On the moon, none of that happens. The moon has no wind, no water, no glaciers, no weather of any kind. What it does have, what it has had for 4.5 billion years, is an endless bombardment of micrometeorites, tiny specks of space rock and debris, ranging in size from grains of sand to microscopic particles, constantly striking the lunar surface at tremendous velocities. When these micrometeorites hit, they vaporize instantly, and the surrounding material gets superheated, shattered, and remelted in a fraction of a second. Then it cools and solidifies again. The result of billions of years of this process is a layer of pulverized material covering the entire lunar surface, sometimes just a few centimeters deep, sometimes several meters deep in older regions. It's called the regolith, and because it has never experienced the smoothing effects of wind or water, its particles are jagged, microscopically, viciously jagged, like tiny shards of broken glass, but smaller, far smaller. The average particle size in lunar regolith is about 70 micrometers. For comparison, a human hair is roughly 70 to 100 micrometers thick. So we're talking about particles that are roughly the width of a single hair, but shaped like shattered glass, and in many cases far smaller. The finest fraction of lunar dust, called submicron particles, can be smaller than 1 micrometer. You cannot see them, you cannot feel them, but you can absolutely inhale them. And here's something that makes this problem even more strange and persistent. Lunar dust is electrostatically charged. On Earth, the constant movement of air and the presence of moisture means that static charges dissipate quickly. But on the moon, in the vacuum, with constant bombardment from solar ultraviolet radiation and charged particles, the dust particles accumulate an electrostatic charge. They become sticky, clinging to surfaces, to equipment, to spacesuits with a tenacity that absolutely baffled the Apollo astronauts. Apollo 17 astronaut Harrison Schmitt a trained geologist and the last human being to walk on the lunar surface, in December of 1972, began suffering what he called lunar hay fever within hours of returning inside the habitat after his first moonwalk. His eyes were watering, his throat was scratchy, his sinuses felt raw. The culprit was almost certainly fine lunar dust that had been tracked in on his suit, then became airborne inside the pressurized cabin when the astronauts took their helmets off. Even after using brushes to clean their suits, the dust had worked its way into every crevice. Apollo astronauts reported that it smelled like gunpowder, sharp and acrid, and that it stained their suits a deeper gray with each successive EVA, no matter how carefully they tried to brush it off. And that was after just a few days on the surface. Now imagine months or years. The health implications of long-term lunar dust exposure are something researchers are actively and urgently investigating. Because here's the comparison that makes scientists genuinely concerned: quartz dust on Earth. Miners and quarry workers who breathe in fine crystalline silica dust over years develop a condition called silicosis, a progressive, irreversible scarring of the lung tissue. The sharp, jagged edges of silica particles pierce the alveoli, the tiny air sacs in your lungs where oxygen exchange happens. Your immune system tries to fight the invasion and fails, surrounding the particles with fibrous tissue instead. Over time, the lungs become stiffer, less efficient, and eventually unable to do their job. Silicosis has no cure. Lunar dust is not identical to silica, but the principle is disturbingly similar. The particles are sharp, they are insoluble, meaning your body cannot break them down. And research supported by NASA's Human Research Program has found that lunar simulants, materials engineered on Earth to approximate lunar dust, are capable of damaging human lung cells and brain cells in laboratory conditions. One study found that lunar dust simulants destroyed up to 90% of human bronchial and neuronal cells in a petri dish. Let that number sit with you for a moment. 90%. Now, a petri dish is not a human body. The concentrations used in laboratory studies are often higher than what an astronaut would be realistically exposed to. Scientists are careful to note that these are early-stage studies and that more research is needed before definitive conclusions can be drawn. But the signal is clear enough that NASA lists lunar dust as one of the 5 highest priority health risks for long-term lunar missions. Not a footnote, not a theoretical concern. One of the top 5, and the mechanical damage doesn't stop at the human body. The Apollo mission reports are full of accounts of lunar dust destroying equipment. The dust worked its way into the joints of astronauts' gloves, making them stiff and difficult to flex. It scratched helmet visors, reducing optical clarity. It clogged filters in life support systems. It abraded the reflective coatings on scientific instruments. NASA engineer Brian O'Brien, who studied the dust problem for decades, once described it as potentially the greatest challenge facing sustained human presence on the Moon. Think about what a permanent lunar base would require. Solar panels to generate power, panels that need to remain clean and clear to function efficiently. In a place where dust clings electrostatically to every surface and is constantly being redistributed by footsteps, vehicle movement and thruster exhaust, keeping those panels clean would be a constant, labor-intensive challenge. Studies suggest that even a thin layer of lunar dust can reduce the efficiency of solar panels by up to 30%. A thicker accumulation can cut power generation in half, and rovers, spacesuits, airlocks, every system that needs to move or seal or transmit light would face constant assault from this material. So how do you fight dust that sticks electrostatically to everything, that you cannot see at its finest scale, and that cuts like glass when it reaches your lungs? Researchers are tackling this from several angles. One promising direction is electrodynamic dust shields. Essentially, surfaces embedded with electrodes that generate a traveling electrical field, pushing charged dust particles off the surface before they can accumulate. Early prototypes have shown real promise in laboratory conditions, removing up to 90% of dust from solar panel surfaces. NASA has been testing this technology as a core component of future lunar infrastructure. Another approach focuses on suit design, developing materials that resist static charge buildup, combined with airlocks that include dedicated dust removal chambers where astronauts can brush, vacuum, and even use ionized airflows to strip dust from suits before re-entering living spaces. And there's a genuinely creative proposal on the table, using lunar dust itself as a building material. The regolith, for all its dangers, is abundant. It's literally everywhere. Using a process called sintering, applying heat or microwave energy to fuse particles together, you can turn loose regolith into solid bricks. The same material that threatens your lungs and your equipment becomes the walls of your habitat, your radiation shielding, even your roads. That is the kind of thinking that makes space exploration feel like hope rather than hubris. But even if we solve the dust problem, engineer suits it can't penetrate, develop shields it can't cling to, build habitats where it can't reach you, we still haven't talked about what happens to your body itself. Not from outside threats, from the inside, from the quiet, relentless unraveling that begins the moment you step away from Earth's gravity, because your skeleton, the framework your entire biology was built around, starts changing the moment you leave this planet. And the moon, with its 1/6 gravity, would put your bones and muscles through a slow-motion crisis that no suit and no shield can protect you from. Let's talk about something that doesn't get nearly enough attention in the conversation about living on the moon. Something that doesn't require a solar storm or a micrometeorite or a dust storm to kill you. Something that works quietly, invisibly, and relentlessly, not from outside your body, but from within it. Your body is betraying you, not out of malice, not because anything has gone wrong, but because the human body is, at its core, an adaptation machine. It is extraordinarily good at tuning itself to its environment. And the moment you set foot on the moon, the moment you step into a world with 1/6 of Earth's gravity, your body begins adapting to that new reality with the same blind efficiency it has always used. The problem is that the reality it's adapting to is one that will eventually make it impossible for you to come home. To understand why, you need to understand something fundamental about how your body works. Something so basic you've never had to think about it, because gravity has always been doing the work for you. Every system in your body evolved under one constant, the pull of Earth's gravity at 9.8 meters per second squared. That number has been true for every ancestor you have ever had, going back hundreds of millions of years. Your cardiovascular system, your skeletal structure, your musculature, your vestibular system, the part of your inner ear that tells you which way is up. All of it was engineered by evolution for exactly one gravitational environment. This one, here, Earth, on the moon, gravity is roughly 1/6 of what it is here. If you weigh 70 kilograms on Earth, you'd weigh just under 12 kilograms on the moon. You could jump roughly 6 times higher than you can here. Moving around would feel effortless, almost dreamlike, and for the first few days, that lightness might feel genuinely wonderful, but your body is already taking notes. Let's start with your bones, because bone is not the static, inert material it might seem. Your skeleton is a living tissue, constantly being broken down and rebuilt in a process called bone remodeling. Specialized cells called osteoclasts dissolve old or damaged bone tissue. Other cells called osteoblasts lay down new bone in its place. This cycle happens continuously throughout your life, and one of its primary drivers is mechanical stress. When you walk, run, climb stairs, or simply stand up against gravity, Your bones experience compressive forces. Those forces signal your osteoblasts to keep building, keep reinforcing, keep maintaining density, remove that signal, or dramatically reduce it, as 1/6 gravity does, and the balance tips. Your osteoclasts keep dissolving bone. Your osteoblasts slow down. The net result is bone loss. This is not theoretical. Astronauts on the International Space Station in the microgravity of low Earth orbit lose roughly 1 to 2% of their bone density per month without countermeasures. In a single 6-month mission, that can add up to a 10% reduction, comparable to the bone loss a person on Earth might experience over a decade of aging. 1/6 gravity is not zero gravity. Your bones would experience more mechanical loading on the Moon than they do on the space station, but it would still be dramatically less than what they need. Research published in MPJ Microgravity suggests that the Moon's gravity is likely insufficient to fully prevent the bone density loss that haunts long-duration spaceflight. The rate would probably be slower than in full microgravity, but it would still be happening every month, quietly, progressively, and bone loss is not just a number on a scan. It means your skeleton becomes more brittle, fracture risk rises. In a fracture on Earth, you get surgery, rest, and rehabilitation in a fully equipped hospital. On the Moon, a serious fracture could be catastrophic. The nearest trauma center is 3 days away by spacecraft. Your muscles tell a similar story, and in some ways, a faster one. Muscle tissue is even more responsive to use it or lose it dynamics than bone. In reduced gravity, your muscles simply don't have to work as hard. The large postural muscles that spend every moment of your Earth life fighting gravity, your calves, your quadriceps, your lower back, find themselves largely unemployed. Without the constant demand, they atrophy, they shrink. Proteins are broken down faster than they're replaced. Astronauts on long-duration missions can lose up to 20% of their muscle mass in just 5 to 11 days without aggressive countermeasures. Exercise protocols on the International Space Station, including resistance training on specially designed machines, can slow this process dramatically but cannot fully stop it. And on the Moon, in habitats that are necessarily small and confined in the early phases of any colony, building and maintaining a comprehensive exercise facility would be both a significant engineering challenge and a daily time commitment of several hours, every single day, for years. Now here's the part that makes this especially unsettling. Your cardiovascular system is next. Your heart is a pump, and like any pump, it calibrates itself to the demand placed on it. On Earth, one of the heart's constant jobs is to push blood upward against gravity, from your legs and abdomen up to your brain and lungs. This requires real cardiac effort and keeps your cardiovascular system in a state of continuous healthy exertion. In reduced gravity, blood redistributes differently. It shifts toward your upper body and head. In the early days of spaceflight adaptation, astronauts often experience what they describe as a head stuffiness, a constant pressure in the sinuses, a feeling that too much fluid has pooled in the upper body. That's not just discomfort, it's your cardiovascular system receiving a false signal, one that says, essentially, the body has too much blood volume. In response, the body does what it's designed to do. It reduces blood volume, suppresses fluid retention, and allows the cardiovascular system to shrink toward a new, reduced demand equilibrium. The result, over months, is a heart that has literally become smaller and weaker. Studies of astronaut cardiovascular health, published in the Journal of the American College of Cardiology, found measurable reductions in cardiac muscle mass and output after extended spaceflight, with some effects persisting long after return to Earth. And then there is something researchers call the fluid shift problem, which is where this gets genuinely alarming and genuinely strange. When fluid shifts toward your head in reduced gravity, it increases the pressure inside your skull. That elevated intracranial pressure pushes against your brain and, critically, against your eyes. The fluid in your skull presses against the back of your eyeballs, flattening them slightly, reshaping the optic nerve and distorting your vision. This phenomenon is called Spaceflight-Associated Neuroocular Syndrome, or SANS. It was first formally identified in astronauts returning from long missions on the ISS, and its prevalence was shocking to researchers. According to NASA and studies published in JAMA Ophthalmology, more than half of male astronauts who spend 6 months or longer in microgravity experience measurable changes to their vision and eye structure. Some of these changes reverse after returning to Earth. Some do not. Several astronauts have returned from long missions to find that they permanently need reading glasses they didn't need before they left. On the Moon, in 1/6 gravity, the fluid shift would be less severe than in full microgravity, but less severe is not the same as absent. In a long-duration stay, perhaps years, the cumulative effect on vision and intracranial pressure remains an open and deeply serious question, one that researchers are racing to understand before Artemis sends humans back to the surface. And finally, perhaps most philosophically unsettling of all, there's the question of what happens to your sense of balance and spatial orientation. Your inner ear contains 3 fluid-filled semicircular canals arranged at different angles, plus 2 structures called the utricle and saccule, which contain tiny calcium crystals called otoliths. These otoliths rest on beds of sensory hair cells, and gravity pulls them downward, telling your brain which direction is down and how your head is oriented in space. Your entire sense of balance, your ability to walk without falling, your capacity to know where your body is without looking. All of it depends on those crystals being pulled by gravity at exactly the right strength. In reduced gravity, the otoliths behave differently. Astronauts in microgravity commonly experience space adaptation syndrome, nausea, disorientation, spatial confusion in the first few days as their vestibular system struggles to recalibrate. On the Moon, the recalibration would be different but still present, and over months and years, the vestibular system adapts to the new gravitational reality. That adaptation is the problem, because if you ever came back to Earth, if you returned after a year on the Moon, your vestibular system, your cardiovascular system, your bones, your muscles would all need to readapt to full gravity. That readaptation is painful, disorienting, and in cases of long-duration exposure, potentially dangerous. Some researchers have raised the question of whether, after enough time in reduced gravity, the process of coming home might itself pose serious medical risks. There may come a point, and this is not science fiction, this is an active area of research and concern, where someone who has spent long enough on the Moon cannot safely return to Earth at all. You would be marooned, not by mechanical failure, not by a broken spacecraft, but by your own transformed biology. The Moon would have remade you into something that Earth can no longer sustain. Let that sit with you for a moment. We haven't even talked about what happens to your mind, because the psychological reality of living on the Moon, the isolation, the confinement, the constant existential weight of knowing that a single equipment failure separates you from oblivion is its own category of challenge entirely. We've talked about what the Moon does to your body, the radiation quietly rewriting your DNA, the dust working its way into your lungs like microscopic broken glass, the bones thinning, the muscles shrinking, the heart growing smaller, the eyes slowly distorting under the pressure of fluid with nowhere to go. All of that is real. All of it is serious. All of it is the subject of active, urgent research by some of the most brilliant scientists and engineers alive today. But none of it, not one single physical threat, is considered by space psychologists and human factors researchers to be the most likely cause of a lunar mission's failure. That distinction belongs to the human mind, because you can engineer a habitat that keeps radiation out. You can design a suit that keeps dust from reaching your lungs. You can build exercise equipment that slows bone loss and maintain a medical protocol that monitors your cardiovascular health. But you cannot engineer your way out of what isolation and confinement do to a human being over time. You cannot build a shield against loneliness. You cannot design a filtration system for existential dread. And on the moon, you would have both. In abundance, let's start with something deceptively simple: distance. Right now, no matter where you are on Earth, whether you're in the middle of the Sahara Desert, on a research station in Antarctica, on a solo sailing voyage across the Pacific, you are at most a few hours away from another human being. The entire surface of Earth is connected. You could, in principle, be rescued. You could, in an emergency, reach help. That knowledge lives somewhere in the back of your mind at all times, and it is a quiet, constant comfort you have never had to consciously acknowledge, because it has always just been true. On the moon, that comfort evaporates. The moon is, on average, 384,000 kilometers from Earth. At the speed of light, a signal takes about 1.28 seconds to travel that distance one way. A conversation has a 2.5-second round-trip delay, manageable but noticeable. More importantly, a spacecraft traveling at the speeds achievable with current technology takes roughly 3 days to make the journey. 3 days. In an emergency, a medical crisis, a catastrophic equipment failure, a psychological breakdown, the nearest help is 3 days away, not 3 hours. 3 days. That is a psychological reality unlike anything any human being has ever had to live with on Earth. And researchers who study isolated, confined environments, Antarctic winter-over stations, submarine deployments, long-duration spaceflight simulations, consistently find that the knowledge of that distance, of that inaccessibility, is one of the most psychologically corrosive forces a human being can face. NASA and other space agencies have studied this extensively. One of the most comprehensive research programs is called HI-SEAS, the Hawaii Space Exploration Analog and Simulation, where volunteer crews live for months at a time in a habitat on the slopes of Mauna Loa volcano on the Big Island of Hawaii, simulating the isolation and communication delays of a deep space mission. What these simulations reveal, consistently and repeatedly, is that the psychological challenges of long-duration confinement are not just real, they are complex, they are unpredictable, and they evolve in ways that are difficult to anticipate or prevent. In the early weeks of a mission, crew morale tends to be high. Everything is new. The mission feels purposeful and exciting. People are focused, motivated, cooperative. Researchers call this the honeymoon phase. But around the midpoint of a mission, something shifts. It has been documented in Antarctic expeditions, in submarine deployments, in spaceflight simulations, and in real long-duration missions on the International Space Station. It's called the third quarter phenomenon. Morale dips, interpersonal conflicts increase. Crew members become more withdrawn, more irritable, more prone to what psychologists call psychological closing in, a narrowing of focus, a withdrawal from the group, an increasing preoccupation with small grievances that would have seemed trivial early in the mission. On a moon mission lasting months or years, the third quarter phenomenon would not be a temporary dip. It would be a sustained reality that mission planners would need to actively and continuously manage. Research published in the journal Acta Astronautica found that among the most significant stressors in isolated, confined environments are monotony, lack of privacy, disrupted sleep, and interpersonal conflict within the crew. Every one of those stressors would be present on a lunar base in concentrated, unavoidable form. Think about the physical environment. A lunar habitat, at least in the early phases of any colony, would be small. Pressurized space is enormously expensive to build and maintain. Every cubic meter of livable volume requires structural material, life support hardware, power, and maintenance. Early lunar habitats, based on current NASA and ESA design concepts, would likely provide each crew member with a living space comparable to a small shipping container. You would share this space with a handful of other people, 24 hours a day, 7 days a week for months at a time. There are no windows to open, no weather to walk out into, no landscape to change. The view outside is always the same grey surface, the same black sky, the same pale blue dot hanging in the void. You cannot go for a walk to clear your head without spending 30 minutes suiting up, at significant physical and operational cost, just to spend time outside in an environment actively trying to kill you. Sleep would be another battleground. The moon's rotation period is about 29.5 Earth days, meaning a lunar day and night each last roughly 14.5 Earth days. If you're living on the lunar surface, there is no natural light cycle to regulate your circadian rhythm. Your body's internal clock, which evolved over millions of years to synchronize with Earth's 24-hour rotation, would have nothing to lock onto. Maintaining healthy sleep in these conditions requires careful management of artificial lighting, strict sleep schedules, and, in many cases, pharmacological support. Disrupted sleep is not just an inconvenience. Studies by NASA and research institutions have found that chronic sleep disruption impairs cognitive function, emotional regulation, decision-making, and immune response. On a mission where clear thinking and calm decision-making could be the difference between life and death, a chronically sleep-deprived crew is not a minor operational problem. It is a potentially existential one. And then there is the question of what psychologists call Earth out-of-view phenomenon. When you are on the moon, Earth is visible in the sky, a stunning, vivid, heartbreakingly beautiful sphere of blue and white and green. It doesn't rise and set the way the sun does from Earth, because the moon is tidally locked, showing the same face to Earth at all times. Earth essentially hangs in the same region of the lunar sky, moving only slightly due to a wobbling called libration. It is always there, always visible, the most beautiful thing in an otherwise barren sky. And that, paradoxically, can make the homesickness worse. There is something profound and disorienting about being able to see your home, to see it in vivid detail, to watch weather systems swirling across its surface, to identify continents, and know that you cannot reach it, that the people you love are right there, a glowing dot you could cover with your thumb, and there is an absolute physical gulf between you and them that no amount of wanting can bridge. Apollo astronauts described a phenomenon researchers now sometimes call cosmic loneliness, a feeling of profound, almost metaphysical disconnection that arrived with unexpected force during their brief journeys. Michael Collins, the command module pilot for Apollo 11, who orbited the moon alone while Armstrong and Aldrin were on the surface, described himself in that moment as the most isolated human being since Adam. He was, by any objective measure, the loneliest person in human history. On the far side of the moon, out of radio contact with Earth and separated from his crewmates, he was the only human being in existence not covered by the disk of either the Earth or the moon. He described the experience as not frightening, but immensely, silently profound. That was for a few hours. Now imagine that feeling not as a passing moment of awe, but as the background frequency of your daily life for months. For years, psychologist Lawrence Palinkas of the University of Southern California, who has spent decades studying human performance in isolated and confined environments, has described the Moon and Mars as presenting psychological challenges that fundamentally exceed anything in previous human experience. Not just in degree, but in kind. The combination of real danger, radical isolation, extreme confinement, disrupted circadian rhythms, communication delays, crew conflict risk, and the relentless sameness of the environment creates a psychological pressure unlike anything that has existed in the history of human exploration. But here is the thing about human beings, the thing that makes this story complicated and hopeful and genuinely astonishing. We have been here before, not on the moon, but in the dark. Human beings have wintered over in Antarctica, in the polar night, in temperatures that make the surface of the moon seem hospitable, in conditions of isolation and confinement that would crush most people. And they have not just survived, they have found meaning there. They have formed bonds of extraordinary depth. They have done science. They have made art. They have laughed and grieved and grown and come home changed in ways they describe not as damage but as revelation. There is something in the human spirit that does not merely endure hardship. It metabolizes it. It turns suffering into insight, isolation into self-knowledge, darkness into perspective. The astronauts and cosmonauts who have spent the most time in space, people like Scott Kelly, who spent nearly a year on the International Space Station, or Valery Polyakov, who spent 437 consecutive days aboard the Mir space station, do not come back broken. They come back different, quitter, sometimes, more deliberate, with a kind of clarity about what matters that most people spend their entire lives searching for and never quite finding. Polyakov, in interviews after his record-breaking mission, said that the experience had taught him something he could not have learned any other way, that the human being is not a fragile thing, that given purpose, given connection, given something worth doing, the mind can adapt to almost anything. He was right, and he was also describing exactly the kind of person who would need to go to the moon, not the fittest, not the most technically brilliant, not even the most courageous, in the conventional action movie sense of that word. The people who will thrive on the moon, who will build something there, who will survive there, will be the ones who have made peace with uncertainty, who can find meaning in monotony, who can be both deeply competent and deeply humble at the same time, who can look at Earth hanging in the black sky and feel awe rather than despair. That is an extraordinary human being, not a superhuman one, but one who has done the internal work that most of us avoid. And maybe that is one of the most unexpected things the moon can teach us, not just about space, but about ourselves, about what we're capable of, about what we're made of, about the difference between surviving and actually living. Because if you can find meaning on the moon, in a metal can, in a grey desert, under a black sky, 384,000 kilometers from everyone you've ever loved, then you can find meaning anywhere. But we're not done. Because even if you solve every psychological challenge, even if you find the right people, build the right systems, maintain the right rhythms of sleep and exercise and connection, the moon still has one more category of threat it hasn't shown you yet. Something that comes not from the moon itself, but from deeper in the cosmos. Something ancient and indifferent and intermittently capable of resetting everything you've built back to zero: space, weather, and one specific type of cosmic event that, if it happened at the wrong moment, could end a lunar colony before anyone even had time to react. Let's talk about the sun, not the warm, life-giving star you think about when you picture a perfect summer afternoon, not the comfortable yellow glow that ripens fruit and powers solar panels and makes everything feel safe and golden. I want to talk about the other sun, the one that astrophysicists and space weather researchers think about when they go quiet and serious in interviews. The one that keeps the people who run power grids and satellite networks and spacecraft operations up at night. The sun is not a stable, predictable object. It is a roiling, churning, violently dynamic ball of plasma, a sphere of ionized gas roughly 1,300,000 times the volume of Earth, held together by its own gravity and powered by nuclear fusion at its core. where temperatures reach 15 million degrees Celsius. Its surface is in constant turbulent motion. Magnetic field lines twist and tangle and snap and reconnect with explosive force. And periodically, unpredictably, with warning times measured in minutes to hours rather than days, it releases energy on a scale that makes every nuclear weapon ever built look like a small candle. These releases come in two primary forms relevant to our story. The first is a solar flare, an intense burst of electromagnetic radiation, primarily X-rays and ultraviolet light, that travels from the Sun to Earth at the speed of light. It arrives in about 8 minutes. On Earth, the atmosphere absorbs the worst of it. On the Moon, there is nothing between you and that radiation pulse. A major solar flare reaching the lunar surface could deliver a significant radiation dose in a matter of minutes, far too fast for meaningful response if you're outside. The second, and far more dangerous, is a coronal mass ejection, or CME. This is a massive bubble of magnetized plasma, sometimes containing billions of tons of charged particles, hurled away from the Sun at speeds ranging from a few hundred to several thousand kilometers per second. When a CME is directed toward Earth, it typically takes between 1 and 3 days to arrive. That's your warning window. 1 to 3 days. Earth handles CMEs through a combination of its magnetic field and atmosphere. The magnetosphere deflects most of the charged particles around the planet, funneling them toward the poles where they create the auroras, the northern and southern lights. What gets through is absorbed and filtered by the atmosphere. The result, for most CMEs, is nothing more alarming than a beautiful light show and some disruption to radio communications and GPS signals. For the Moon, a CME is something categorically different. With no magnetosphere and no atmosphere, the full force of a coronal mass ejection strikes the surface directly. Every charged particle in that plasma cloud hits the lunar soil and anything on it, without filtration, without deflection, without mercy. Now, let me tell you about the Carrington event. On September 1st and 2nd of 1859, the largest solar storm in recorded history struck Earth. It was observed by British astronomer Richard Carrington, who was sketching sunspots through his telescope when he witnessed a sudden, blindingly bright flash of white light near a cluster of sunspots, a solar flare of extraordinary magnitude. 17 hours later, far faster than typical CME transit times, because the plasma was ejected at exceptional velocity, the resulting coronal mass ejection slammed into Earth's magnetic field. What happened next was, by the standards of 1859, a spectacular curiosity. Auroras were visible as far south as Cuba and Hawaii. Telegraph systems across North America and Europe failed catastrophically. Some telegraph operators reported receiving electric shocks from their equipment, and some lines continued transmitting messages even after operators disconnected the batteries, powered entirely by the induced current from the geomagnetic storm. People in the northeastern United States reportedly woke up in the middle of the night thinking it was dawn because the auroral light was so bright. In 1859, the world's technological infrastructure was limited to telegraph lines. The damage, while dramatic, was manageable. Now ask yourself, what would the Carrington event do today? A 2013 study commissioned by Lloyd's of London and the Atmospheric and Environmental Research Institute estimated that a Carrington-scale event striking Earth today could knock out electrical power for 120 million to 160 million Americans for periods ranging from 16 days to 2 years, depending on the extent of transformer damage. The economic cost was estimated at between $0.6 trillion and $2.6 trillion. Satellites would be disabled or destroyed. GPS would fail. Communication networks would be severely disrupted. The cascading effects on water systems, food supply chains, hospital operations, and financial systems would be profound. That is what the Carrington event would do to Earth, with its magnetosphere and atmosphere providing substantial protection on the Moon with no protection whatsoever. A study published in Space Weather Journal estimated that a Carrington-scale event on the lunar surface could deliver a radiation dose of approximately 10 gray, a unit of absorbed radiation energy, to an unshielded person on the surface. For context, a dose of 4 to 5 gray to the whole body is considered the LD50, the dose at which 50% of exposed individuals die within 60 days without medical treatment. 10 gray is roughly twice that. It would be rapidly and severely lethal, and there is almost no warning. Current space weather monitoring systems, including NOAA's Deep Space Climate Observatory, known as DSCO-VR, positioned at a gravitational balance point between Earth and Sun, called Lagrange Point 1, can detect incoming CMEs and provide between 15 minutes and a few hours of warning before they reach Earth. That is barely enough time for power grid operators to take protective measures. For a crew outside on the lunar surface, a warning time of 15 minutes might not even be enough to get back inside a habitat, let alone reach a purpose-built radiation shelter deep enough to offer meaningful protection. Now, to be fair, the probability of a Carrington-scale event on any given day is low. Researchers estimate that an event of that magnitude occurs perhaps once every 100 to 150 years, based on the historical record and analysis of solar activity cycles. We are statistically overdue. The last Carrington-scale event was in 1859, and we've had several near misses since, including a significant CME in July of 2012 that narrowly missed Earth by about 9 days in orbital terms. Had that CME been directed at Earth, researchers at NASA estimated it could have been comparable to or stronger than the Carrington event. The risk on any given day is low. But a lunar colony is not a single day, it is years, decades, and over decades, the probability of encountering at least one major solar storm event becomes disturbingly significant. There's another layer to this that rarely gets discussed: solar energetic particle events, or SEEBs. These are smaller than a full Carrington-scale CME, but still capable of delivering dangerous radiation doses to unprotected individuals on the lunar surface. And they happen far more frequently, multiple times per year during solar maximum, the peak of the Sun's roughly 11-year activity cycle. We are currently approaching and entering solar maximum. Solar cycle 2045, which began in December of 2019, has been more active than many scientists predicted. NOAA's Space Weather Prediction Center has noted that Cycle 25 has already produced several significant flare and CME events, and activity is expected to remain elevated through the mid-2020s. The Artemis program, NASA's initiative to return humans to the Moon, is targeting lunar landings in this same time window. The people who will first set foot on the Moon in the modern era may do so during one of the most active solar periods in recent decades. So what's the solution? How do you build something on the Moon that can survive a serious solar storm? The most promising answer is one that sounds almost poetic in its simplicity. You go underground. The Moon's surface is covered in lava tubes, enormous underground tunnels formed billions of years ago when lava flowed beneath a solidified crust and then drained away, leaving hollow channels sometimes hundreds of meters wide and kilometers long. Data from the JAXA Selene mission, as well as analysis published in the journal Geophysical Research Letters, has confirmed the existence of at least one large subsurface void near the Marius Hills region of the Moon's near side, a structure that could potentially be large enough to house a small city. Underground, beneath meters of rock and regolith, radiation from solar events is dramatically attenuated. The same material that makes lunar dust a surface hazard becomes, in sufficient thickness, a radiation shield. A habitat built inside or beneath a lava tube structure would be protected from solar storms in a way that no surface structure could match. It would also provide more stable temperatures, protection from micrometeorite impacts, and a degree of structural integrity that surface habitats exposed to the thermal expansion and contraction of extreme temperature cycles would struggle to achieve. Building underground is technically complex. Accessing and preparing a lava tube for habitation would require robotic precursor missions, careful geological survey, and engineering solutions that don't fully exist yet. But the principle is sound, and several research groups, including teams at the European Space Agency and various university programs, are actively working on what a subsurface lunar habitat might look like. There's also ongoing research into personal radiation protection, wearable shielding technologies that could provide astronauts caught outside during a solar event with some degree of protection while they make their way to shelter. And early warning systems are being improved, with proposals for additional monitoring spacecraft positioned between Earth and Sun to extend warning times from minutes to hours. None of these solutions are complete, none of them are deployed, and none of them solve the fundamental reality that the Sun is an unpredictable and occasionally catastrophic neighbor, and the Moon has no natural defense against it whatsoever. But here is what I find remarkable about all of this. Every single problem we have discussed in this series, the vacuum, the temperature extremes, the radiation, the dust, the bone loss, the psychological pressure, the solar storms is a known problem, a documented, studied, researched, actively being worked on problem. The fact that we know about these threats in such detail is itself a testament to the extraordinary work of thousands of scientists, engineers, and astronauts over the past 6 decades. The Carrington event could have remained an obscure historical footnote. Instead, it became a case study, a warning that space weather researchers have spent decades using to model worst-case scenarios, develop monitoring systems, and design protective infrastructure. The bone loss problem could have been discovered only after astronauts returned unable to walk. Instead, it was identified, studied on the space station, and is being actively countered with exercise protocols, pharmacological interventions, and habitat design improvements. Every chapter of this story is also a chapter of human ingenuity, responding to the universe's indifference. The Moon is not trying to kill you. It's simply being what it is, an ancient, airless, unprotected rock in a violent cosmic neighborhood, following the laws of physics with perfect impersonal consistency. It doesn't care whether you live or die. It has no opinion on the matter. We are the ones who care. We are the ones who study and plan and build and test and fail and try again. We are the ones who look at a world that seems designed to kill us and ask, what would it take? There is one more category of threat we haven't addressed yet. One that is less dramatic than a solar superstorm, less visceral than radiation sickness or bone loss, but that some researchers consider the single most underrated long-term danger facing any permanent lunar settlement. It has to do with resources, with water, with the razor-thin margin of survival that any closed-loop life support system must maintain, and what happens when that margin is breached. On the Moon, that breath is an engineering problem of staggering complexity. Every molecule of oxygen you inhale on a lunar base has to come from somewhere. Every molecule of carbon dioxide you exhale has to go somewhere. Every drop of water you drink, every calorie of food you consume, every gram of waste your body produces, all of it exists within a closed system with no natural replenishment, no margin for significant loss, and no tolerance for failure. This is the life support problem. And it is, in many ways, the most mathematically unforgiving challenge in all of human space exploration. Let's start with the numbers, because the numbers are clarifying. The average adult human being consumes approximately 550 liters of oxygen per day. They exhale roughly 200 grams of carbon dioxide. They need between 2 and 3 liters of water for drinking alone, more when you account for the water used in food preparation, hygiene, and the water content of food itself. They produce roughly 1 kilogram of solid waste per day and several liters of liquid waste. They need somewhere between 2,000 and 3,000 calories of food energy daily. Multiply that by a crew of 6. Multiply it by 365 days. Multiply it by the number of years you're planning to sustain the colony. The numbers become enormous very quickly. In the early days of human spaceflight, the solution was brute force. Bring everything you need from Earth and plan the mission to last only as long as your supplies. The Apollo missions were masterpieces of this approach, precisely calculated, limited in duration, with every consumable carefully measured and packed before launch. Apollo 17, the longest lunar surface mission, lasted just under 75 hours on the surface. The life support system needed to sustain 3 human beings for about 12 days total round trip. A lunar colony cannot work this way. The cost of launching mass from Earth's surface to the Moon is extraordinary. Current estimates place the cost of delivering 1 kilogram of payload to the lunar surface at somewhere between $10,000 and $1 million, depending on the launch vehicle and mission architecture. Resupplying a colony of 6 people for a year at current costs would require delivering several tons of consumables, water, food, oxygen, at a financial cost that makes even the most ambitious space program budgets look inadequate. The only viable long-term solution is a closed-loop life support system, a system that recycles, that takes the waste products of human metabolism and converts them back into usable resources, that captures the carbon dioxide you exhale and splits it back into oxygen, that reclaims the water from your urine, your sweat, your breath, and makes it drinkable again. The International Space Station is the most advanced operational closed-loop life support system ever built, and it is worth understanding both what it achieves and where it falls short, because those gaps are the same gaps a lunar colony would need to close. The ISS uses a system called the Environmental Control and Life Support System, or ECLSS. Its water recovery system reclaims water from urine, humidity condensation, and crew perspiration through a multi-stage filtration and purification process. According to NASA, the current system recovers approximately 90 to 93% of available water, an impressive figure, but one with important caveats. That remaining 7 to 10% is lost. On a long-duration mission with no resupply, that loss accumulates. Over months and years, you are slowly bleeding out your water supply. Oxygen on the ISS is generated primarily through a process called electrolysis, passing an electrical current through water to split it into hydrogen and oxygen. The oxygen is released into the cabin atmosphere. The hydrogen is currently vented to space, a loss that requires ongoing water resupply to compensate. A truly closed system would need to find a use for that hydrogen, or find a way to recover it. Carbon dioxide scrubbing on the ISS uses a system called the Carbon Dioxide Removal Assembly, which captures CO2 using absorbent materials. A separate system called the Sabatier reactor then combines that CO2 with the hydrogen from electrolysis to produce methane and water, recovering some of the water and providing a partial closure of the loop. But the methane is currently vented to space. Again, a loss. Again, a system that is not fully closed. NASA's research into next-generation life support, conducted under the Advanced Life Support Program and documented extensively in technical literature, identifies closing these loops completely as one of the central engineering challenges of long-duration deep space exploration. Current systems on the ISS achieve what researchers call a closure rate of perhaps 90 to 95% for water, For a mission that lasts years on the Moon, that remaining 5 to 10% leakage is not acceptable without substantial resupply. But here is where the Moon offers something genuinely remarkable, something that, if it can be accessed and utilized at scale, changes the entire equation: water ice. For decades, scientists suspected that water might exist in permanently shadowed regions near the lunar poles, craters so deep and so angled that sunlight has never reached their floors in billions of years. In these places, temperatures drop to around -170 to -200 degrees Celsius, among the coldest stable environments in the entire solar system, cold enough to trap and preserve volatile compounds, including water ice, that would otherwise evaporate in the harsh lunar environment. That suspicion became confirmation. Data from NASA's L-Cross mission in 2009, which deliberately crashed a rocket stage into a permanently shadowed crater near the lunar South Pole and analyzed the resulting plume, detected water ice unambiguously. Subsequent analysis of data from multiple missions, including NASA's LRO and India's Chandrayaan missions, has refined those estimates. A landmark study published in Nature Astronomy in 2020 confirmed the presence of water molecules on sunlit portions of the lunar surface as well, not just in permanently shadowed regions detected by NASA's SOFIA Airborne Observatory. The estimates of how much water ice exists at the lunar poles vary widely, from millions of tons to potentially billions of tons, depending on depth and distribution. The uncertainty is large because we have not yet drilled, sampled, or directly measured the polar deposits at depth. We have orbital and impact data. We do not yet have ground truth. But even the conservative estimates are significant. If accessible, lunar water ice could be electrolyzed into hydrogen and oxygen, providing both breathable air and rocket propellant. It could be purified for drinking. It could be used in life support systems. It could, in principle, provide the resource foundation for a self-sustaining human presence. The word "if" is doing an enormous amount of work in that sentence. Accessing water ice in permanently shadowed craters is technically formidable. These regions receive no sunlight, which means no solar power, the primary energy source for most proposed lunar infrastructure. Temperatures there are brutal even by lunar standards. The terrain is uncharted at ground level and potentially treacherous. Mining and extracting ice from regolith, purifying it, and integrating it into a life support system at meaningful scale is an industrial operation, not a scientific one, and the industrial infrastructure does not yet exist. And food. Let's talk about food, because it is perhaps the most emotionally loaded resource of all, and the one whose supply chain is least advanced. A lunar colony cannot be fed from Earth indefinitely. The mass required, the cost of delivery, and the simple logistics of resupply make long-term dependence on Earth-grown food unsustainable. At some point, a permanent lunar presence must grow at least some of its own food. This is where the concept of bioregenerative life support comes in, using plants, algae, or other biological systems to simultaneously produce food, recycle carbon dioxide into oxygen, purify water through transpiration, and manage waste. It is, in a very real sense, recreating a miniature version of Earth's biosphere inside a habitat. The NASA-funded Veggie program, which has been growing plants on the International Space Station since 2014, has demonstrated that it is possible to grow leafy greens, lettuce, kale, radishes, mustard in microgravity under artificial light. Astronauts on the ISS have eaten space-grown food multiple times, and the psychological boost of tending living plants and eating fresh food in an otherwise sterile metal environment has been documented as significant, arguably as important for crew morale as the nutritional value. But leafy greens are not a complete diet. Growing calorie-dense staples, wheat, rice, potatoes, soybeans, at the scale needed to meaningfully supplement or replace Earth-supplied food requires far more volume, far more energy, and far more technical sophistication than growing a tray of lettuce. A study published in Open Agriculture estimated that feeding a crew of 6 entirely on space-grown crops would require a growing area of roughly 40 to 50 square meters per person, a total of 240 to 300 square meters of pressurized, lit, climate-controlled growing space per crew. That is an enormous amount of infrastructure for a facility that is itself already extraordinarily expensive to build and maintain. And then there is the soil, or rather the lack of it. Lunar regolith is not soil. It contains no organic matter, no microbial life, none of the complex biological ecosystem that makes Earth's topsoil one of the most productive and irreplaceable substances on the planet. Growing plants in lunar regolith would require substantial amendment, adding nutrients, organic material, beneficial microorganisms. A study published in Communications Biology in 2022, in which researchers at the University of Florida actually grew plants in real lunar soil samples returned by Apollo missions, found that plants did germinate and grow, but slowly, with signs of significant stress, and with considerable variation depending on the specific regolith sample used. It was a proof of concept, not a production system. The path from we can grow a stressed plant in a petri dish of moon dirt to we can feed a colony of hundreds from lunar agriculture is long, technically complex, and full of unsolved problems. So here is the picture that emerges when you look at all of this together. A lunar colony's survival depends on a chain of interdependent systems: life support, water recovery, oxygen generation, food production, waste management, each of which must function reliably, simultaneously, and with minimal loss for months or years at a time. Each of these systems is complex, each has failure modes, and in a closed system, the failure modes interact. A breakdown in water recovery affects oxygen generation, which affects food production, which affects crew health, which affects the ability to maintain and repair the other systems. Engineers call this kind of interdependency a single point of failure cascade. It is the scenario that keeps life support system designers awake at night. On Earth, you are embedded in a planetary life support system of almost incomprehensible redundancy and resilience. If the air in your city gets polluted, the atmosphere is so vast and well mixed that clean air is never far away. If your local water supply fails, you can get water from somewhere else. If your food supply is disrupted, there are other farms, other regions, other countries. The Earth's biosphere has been running its life support systems for nearly 4 billion years, and it is robust beyond anything human engineering has yet achieved. On the Moon, you are running a prototype version of that system, built from scratch by human beings, in a facility the size of a small building with a crew that cannot afford a single catastrophic failure. The margin is real, it is thin, and holding it requires not just brilliant engineering, but the kind of relentless, disciplined, practiced operational excellence that is itself a form of art. And yet, and I say this with genuine wonder, not false optimism, human beings are extraordinarily good at this. The International Space Station has been continuously inhabited since November of 2000, more than 2 decades, without a single loss of crew life due to life support failure. It has had close calls, it has had equipment malfunctions, it has had moments where the margin got very thin indeed. And every time, the combination of well-designed systems, well-trained crew, and well-supported ground teams has held the line. That record is not luck. It is the product of thousands of engineers and astronauts and mission controllers who understood the margin and protected it with everything they had. The Moon will demand that same level of excellence. And then it will demand more. There is one more layer to this story that we haven't touched yet. something that sits above all the individual physical and psychological and engineering challenges we've discussed. A systemic vulnerability that could undermine everything, not through equipment failure or solar storms or dust or bone loss, but through a failure of a different kind entirely, a failure of governance, of international cooperation, of the political and legal frameworks that determine who gets to be on the moon, who owns what's there, and what happens when the interests of different nations and corporations and factions collide in a place where there is no law enforcement, no judiciary, and no exit. So here we are. We've walked through the vacuum and the temperature swings, the invisible radiation quietly rewriting your DNA, the microscopic glass-like dust that never stops clinging, the bones that thin and the heart that shrinks, and the eyes that slowly lose their shape. We've sat with the silence of 384,000 kilometers of empty space, felt the weight of a mind trying to hold itself together in a metal can under a black sky, and stared down the barrel of a sun that can, without warning, erase everything you've built in a matter of hours. We've traced the razor-thin arithmetic of every breath, every drop of water, every calorie keeping a human being alive in a place that was never designed to support life. And through all of it, every terrifying, humbling, awe-inspiring chapter, one thing has remained constant. We are still here, still studying, still building, still asking what it would take. Because that's what human beings do. We don't look at the impossible and walk away. We look at it, we understand it as deeply as we can, and then we get to work. The moon is not an invitation, it is a test, and the fact that we are already preparing to take it seriously, rigorously, with full knowledge of the cost, might be the most extraordinary thing about us. If you made it this far, thank you, genuinely. Now go look up at the moon tonight and see it for what it really is.